Alright, hi guys. We'll be covering chapter 11, thermal properties of matter. Now I'll be first to tell you that this chapter is going to be the most mathematically involved you will encounter in your set 3 year. It will be challenging because there's a lot of new definition, but the concepts are simple enough, I would say. So without further ado, let's just carry on with the chapter. Right, these are the things that we'll be covering: heat capacity, specific heat capacity, melting, solidification, boiling, condensation, latent heat, and specific latent heat, and evaporation. Alright, so what are the things that will be covered today? Now, before we begin our study, it becomes important for us to recall what we have learned, because these few points will be important for your study of this chapter. Right, so first point you need to remember: particles are always in continuous random motion, and there exist attractive forces between these particles. Point 2, you learn this in kinetic model of matter. The higher the temperature of the object, we say the kinetic energy of the molecules that compose of the object is higher, and the molecules are consequently also moving faster. Right. Point 3, we cover this in work energy power, principle of conservation of energy. Energy cannot be created or destroyed. Energy can only be converted from one form to another. So this will become important in our study later on when we start doing our calculations. Alright, point 4, thermal energy moves from high temperature to low temperature. This will be important again for our calculation. And oftentimes in this chapter we always quote this formula we learn in work energy power, which is energy equals to power times time. Alright, so the very first portion that we'll be covering or we'll be discussing today is the concept of internal energy. Now, all molecules have energy, and collectively we call this energy in physics or in the study of thermal properties as internal energy. Now, internal energy composed of two parts: the kinetic energy and the potential energy. Now, kinetic energy, you already learned all of this in kinetic model of matter. We know that the higher the kinetic energy of the molecules, the higher the speed, they move faster, and the higher the kinetic energy, the higher the temperature of the object. Now, later on we'll be covering a concept called heat capacity. It is to do with temperature change. Now, the second portion that makes up internal energy is the potential energy. So we say when an object has a higher potential energy, or I'm increasing the potential energy, what it is doing is overcoming the intermolecular forces of attraction or interatomic forces. Alright, when you overcome these forces, then you have a change of state. Alright, how to calculate or how to deal with calculations involving change of state, we use a concept later on called the latent heat. Now, the first portion we'll just be covering and discussing this. The later on we'll be covering and discussing this, and then later on there will be questions that you have to draw on both of them to deal with or to obtain your answer. Now let's talk about heat capacity. What is that exactly is heat capacity? Heat capacity, written or short form as a big C, capital C, is the amount of thermal energy required to raise the temperature of an object by 1 degree Celsius or 1 Kelvin. Alright, we always write it as Q equals to C, big C delta theta. Alright, Q is the amount of energy required, C is the heat capacity here, and delta theta together is known as the change in temperature. Alright, so the units of Q, which is energy, is joule. The units of C, which is the heat capacity, is joule per degree Celsius or joule per Kelvin. Unit of change in temperature is of course just degree Celsius or the Kelvin. Alright, so this formula is important. Q equals to C delta theta. So please remember this. Now, how do we deal with heat capacity, and what on earth is heat capacity? Now, so let's say I have 100 grams of water, and I tell you that if I supply 12,600 joules of energy, the temperature change observed is 30 degrees Celsius. So the heat capacity then tells us how much energy is required to change this object by 1 degree Celsius. Alright, the formula is Q big C delta theta. So if the energy is 12,600, C, the change in temperature is 30 degrees Celsius, then all I do to find big C is C equals to Q over delta theta, which is what they did here. So Q is the energy, 12,600 divided by the temperature change produced, 30 degrees Celsius, and I get that it requires 420 joules of energy to change or increase the temperature by 1 degree Celsius. Now, if I have another object that is just twice this fellas in terms of mass, 200 grams, then I will realize that actually I will need a higher heat capacity, because if I need 420 joules to raise an object of 100 grams by 1 degree Celsius, that it makes logical sense for me to require double the amount of energy if I have double the amount of the mass of the object. So mass is a factor that affects the heat capacity. Now, what other factors affect heat capacity? The type of objects also affect the heat capacity. Now, water is one of those objects that has very high heat capacity compared to other materials. Alright, that means I need to supply so much more energy. I need to supply 420 joules of energy to increase the temperature of this 100 grams of water by 1 degree Celsius. Compared to copper, I only need 38.5 joules of energy to increase the temperature by 1 degree Celsius. Alright, so material, of course, is going to be another factor that affects heat capacity. Now, we learn now the concept of specific heat capacity. Now, specific heat capacity is basically heat capacity per unit mass. Now, it is not that useful for us to compare the heat capacities of different materials, especially if we have materials that are made out of so many different materials and of different concentration of the material, such that the masses of each individual component is different. So we have a standardized set of values for each different material, and that will allow us to do the calculation much more simply. So the concept of specific heat capacity is simple. It is heat capacity per unit mass. In other words, specific heat capacity is also written as small c, as opposed to heat capacity, which is written as big C. Alright, so this is heat capacity, this is specific heat capacity. So specific heat capacity tells me how much energy I need to increase 1 kilogram of the object, or 1 unit mass of the object, by 1 degree Celsius. So this is the unit of heat capacity, joule per kilogram degree Celsius, or joule per kilogram Kelvin. Q is the energy required, is joules, mass in kilogram. Delta theta, of course, is still the change in temperature, so it is given as degree Celsius or Kelvin. Now, you just now earlier learned that the formula for heat capacity and energy is Q equals to big C delta theta. Just take note, this one is heat capacity. So, since specific heat capacity is heat capacity per unit mass, therefore, if I were to change this big C here in this formula with MC, substitute MC, I will get the formula involving the specific heat capacity, which is Q equals to MC delta theta. So I now have two formulas, Q equals to MC delta theta and Q equals to C delta theta. Alright, so this one you must ingrain into your memory. The definitions you must ingrain into your memory, because if not, you're going to have difficulty later on in the chapter. Alright, so let's look at some specific questions that we can do, some examples. Alright, specific heat capacity. 100 grams of water. Let's say the thermal energy needed to increase the temperature by 1 degree Celsius is 420 joules. So, if I am calculating per unit mass, so if I needed 420 joules to increase 1 degree Celsius, by 1 degree Celsius, 100 grams of water. So how much energy do I need to raise the temperature by 1 degree Celsius for 1 gram of the object? So then I just take 420 joules divided by 100, that will give me the amount of energy. Now, just to be slightly careful, Q equals to MC delta theta, the C can be given as joule per gram degree Celsius, or can be given as joule per kilogram degree Celsius. So depending on what you are given or what you are asked to calculate, please make sure that correspondingly you use your mass in grams or in kilograms. So just be careful. If they give your specific heat capacity as joule per degree Celsius, kg degree Celsius, then make sure that your mass that you use in the calculation is in kilogram. So let's have a look at how a specific heat capacity question will look like. Alright, so simple question. I got a question where they ask you to calculate the amount of heat or energy required to raise the temperature of 100 grams of ice from -20 to -5 degrees Celsius. And I'm given the specific heat capacity is 2000 joules per kilogram Kelvin. So again, I just use the formula Q equals to MC delta theta. Q is the amount of energy I require, or the heat in this question that they ask. The mass is 100 grams, but I just be careful. I do a quick check. I notice that the specific heat capacity is in kilograms. So make sure that you change this to 0.1 kg. Alright, specific heat capacity is 2000 joules. The temperature change is -20 to -5 degrees Celsius, which is actually a 15 degrees Celsius temperature change. Then I can calculate. It just gives me the value 3000 joules. So this is how we calculate, or you deal with calculation involving specific heat capacity. Now, moving on to another question involving specific heat capacity. We have, just now I told you that this formula will be used quite often in this chapter. Alright, so just take note. We have specific heat capacity, or they ask you to calculate the specific heat capacity of aluminum, given that the heater rated at 30 watts, which means the power is 30 watts, takes 5 minutes to increase the temperature of 450 grams of aluminum from 27 to 50 degrees Celsius. So first off, what I do is I calculate the energy given out by the heater, a 30 watt heater, in 5 minutes time. So remember that when you do calculations of energy, power and time, that you should change the time to seconds, which is the base SI unit. So when you do the calculation, you will get the answer that this is 9000 joules. Now, 9000 joules is the amount of energy required to raise 450 grams of aluminum by from 27 to 50 degrees Celsius. So 9000 joules. Q equals to MC delta theta, the amount of energy. The mass of the aluminum is 450 grams. So depending on whether I want to calculate the specific heat capacity in grams or kg, in this case I chose to change it to kg, so my final answer would therefore be in kilograms. So I do, and the temperature change produced is from 27 to 50 degrees Celsius, which is a difference of 23 degrees Celsius. I just do a quick calculation. C is then equals to 9000 over 0.45 times 23, and I'll get that the answer is 870 joules per kilogram degree Celsius. Alright, another quick question. Now, this question type is a little bit more challenging. It's a question asking when I have two objects that are where I'm mixing them together. So have a quick read of the question. I got a hot coal, 50 grams of hot coal, and the temperature of the coal is at 200 degrees Celsius. So I've written this down here, and I dropped that coal into 150 grams of water, which is at 25 degrees Celsius. Then they ask you what is the final temperature reached. Alright, so now you remember at the start I asked you to remember that there were 5 important points, so we have to use some of them. Let's think about how to solve this question. I got an object 200 degrees Celsius, 50 grams, and then I'm going to mix that with an object that is 150 grams and 25 degrees Celsius. So one is hotter, one is colder. Of course, thermal energy is going to flow from here to here. So I expect that this fella, the temperature is going to drop. While the 25 degrees Celsius, I expect that the temperature would increase. So that's all I need really to go and solve. I do not know the final temperature, so I do need to kind of set up the problem. Now, the difficulty in this chapter is the setting up of the problem. You need to be able to describe using principle of conservation of energy, what are the energies involved. So let's look at what are the energies involved. One, the energy of the coal will actually lose energy because the temperature will decrease, while the water here will actually gain energy. So the energy lost by the coal will be the energy gained by the water. So and then if there are no other energies involved, then I can just use this statement and solve. I just need to plug in the correct values. So MC delta theta is equals to MC delta theta. Then you're going to tell me, hey, wait, actually I don't know the final temperature. So how can I tell what is the temperature difference here? I mean, 200 degrees, the temperature is going to drop to some unknown value. I don't know what is this value. This value, 25 degrees, the temperature is going to increase to this value. Then after that, they will reach an equilibrium and the temperature will stop changing. So how to solve this kind of problem? It appears sometimes in the O levels, so you can just take note of this. I just let the final temperature be T. Let final temperature be T, and then you can solve it. Alright, so just be careful when you're plugging in. There's a lot of numbers that you have to plug in here, so make sure that you use the correct values for the correct portion. So mass of the coal is 50 grams, so make sure that you use correct value because it is given in kilograms here, the specific heat capacity. I would then decide to use the mass in kg. So I use the mass of the coal in kg. 50 grams to kg is 0.05 kilograms. The specific heat capacity of coal is given as 710. The temperature difference, I don't actually know. I know that initially it was 200, then it dropped down to T degrees Celsius. So my final temperature return is 200 minus T, because that is the temperature difference produced. For the water, then the mass of the water is 150 grams, so make sure you convert it to kilogram, 0.15 kg. The C of water is given as 4,200 joules. I'm going to run out of space, sorry for the mess. And the temperature difference is actually initially 25, then it became T. So the temperature is actually, it's going to be messy here, T minus 25. That is the temperature difference produced. So then it's all just a matter of math. This is the statement you have formed. Now it's all just a matter of math for you to solve. So I'm just going to do the math for you. So multiply this is 35.5, 200 minus T. Multiply these two, I will get 630. Then this one just translates down T minus 25. Alright, do your proper expansion. You will get 7100 minus 35.5 T. Just multiply here and multiply here. Then 630 T minus, do your multiplication, 15750. Bring all the terms with T to one side, bring all the terms without T to the other side. Do a quick solve. You get 665.5 T is equivalent to 22850. Solve for T and you get the temperature as 34.3 degrees Celsius. Now, this question allows you to do a little bit of check. When you have this kind of question, does it make sense, this value? Is the temperature somewhere in between 200 degrees Celsius and 25 degrees Celsius? Yes, then you probably got the correct answer here. So just take note of how to solve this kind of question. It is not so common, but it's possible for it to come out in the O's. Now, I am not going to go through all the questions and solutions of the questions, of the examples given in the notes, but you can just have a look at them. I'm going to leave it on the screen for a while so you can have a look at each of the slides. I'm going to move on to the next portion of the chapter because now the video will be too long. So just have a look. Alright. This is the next page. Alright, this is the next slide. Alright, please, you can just pause the video at any time, have a look at the solutions and the answers given in the examples. This is the next slide. Alright, this is the next slide, question. This is the next slide. And we'll come to the next portion of the chapter. Now the next two portions of the chapter are linked together: melting and solidification, and boiling and condensation. And it will be brief because I do not think there are quite a lot of content to cover. So let's discuss melting and boiling. So how does one discover the melting point of ice? It must be pure melting ice. You should have learned this in the temperature chapter. It must be pure melting ice. You put a thermometer in ice, but then you must wait for the ice to melt, then you record the temperature. That will be the ice point. Alright, because you need to be clear. Students often have this misconception that the ice can only exist at 0 degrees Celsius. Ice starts forming at 0 degrees Celsius, but ice can exist at any temperature below 0 degrees Celsius. You can have ice at negative 100 degrees Celsius even. Alright, so now this should not be too unfamiliar for those of you who take chemistry. This is called the heating curve. Now this portion here describes the object when it is in solid. So the temperature is increasing. Now as you increase the temperature of water, which melts at 0 degrees Celsius, of water from negative 15, negative 10, the temperature will increase normally until it hits the melting point. Then at the melting point, if you are heating the object, you will stop there and it will proceed with melting. Then once all the ice has melted or changed to liquid, then the temperature increase will then resume again. Now, we break this down so that it's easier for us to analyze. The portion here where the ice is increasing in temperature, we say the kinetic energy or energy is being supplied to the kinetic energy of the molecules, which means the energy that is being supplied by the heater goes purely into the kinetic energy and causes the increase in temperature. We learned this in the internal potential and kinetic energy at the start. Alright, at the point where it is melting or it has reached the melting point, then we say all the energy is only going into the potential energy. And what is it being used for? It's used to overcome intermolecular forces of attraction and results in a change of state. Once all of the object has melted or the water has melted, then it proceeds to the increase in temperature and the kinetic energy increase. Now, this slide, I put a star here because all of these portions are important. Now, again, whatever I've explained is just all over here. This is a common O-level question that appears. They ask you, why is there no temperature change over here when the change of state is occurring? And the answer is actually over here. Alright, there's no temperature change because all of the energy goes into the potential energy. You say this first. And what is being used? What is it being used for? It's used to change state by breaking or overcoming any of the intermolecular forces of attraction or the strong bonds between the particles of the solid ice. You can use this, but you can use intermolecular forces of attraction. Since all the energy goes into the total, so this is the second point, since all the energy goes into the potential energy, none goes into the kinetic energy, so it does not increase. Because none goes into the kinetic energy, the temperature remains constant. So this is how you will explain why there is no temperature change when a change of state is occurring. Now, an important point to note, this is going to be the first time I'm going to introduce to you, the thermal energy absorbed, but the amount of energy absorbed during this process of change of state, of melting, specifically is called the latent heat of fusion. So during melting, we call that latent heat of fusion. Alright, okay, again, I won't talk about the freezing point on naphthalene. You can just go and have a read of it. How does one determine the freezing point? Again, it is the same kind of concept. Instead of having a heating curve where the temperature is going up, I have a cooling curve where the temperature is going down. Again, whenever there's a change in temperature, we say the kinetic energy is being changed. Whenever there's a change of state, I say the potential energy is changing. Again, once all the change of state has occurred and it has become solid, then I say the energy now goes all into the kinetic energy, which results in the temperature change. I won't explain this because it's literally the same as the melting process. Solidification is just the opposite of the melting process. So instead of overcoming the intermolecular forces of attraction, it is now forming intermolecular forces of attraction. So again, total internal potential energy decreases, so no change in Ke, that's why the temperature remains constant. Alright, so the thermal energy that is released again is called the latent heat of fusion. Now, the boiling and condensation portion is exactly the same as melting and solidification, except solidification is called freezing also, by the way. So boiling and condensation is exactly the same, except it entails a change of state between gas and liquid. So gas to liquid, liquid to gas, sorry, is called boiling. Condensation is gas to liquid. Alright, so I'll just show you the slides because it's literally the same few things that you will see over and over again. Alright, I'll stop at the important parts. So a few things when you are trying to define boiling. Boiling is a change of state from liquid to gas without a change in temperature. This portion is important. A lot of students forget this, so please remember, I put a double star here. This energy that is entailed by the change of state is called the latent heat of vaporization. The energy used up in the boiling process is called the latent heat of vaporization. Alright, so just now you had latent heat of fusion. So latent heat of fusion entails change of state between solid and liquid, while vaporization between liquid and gases. Be it liquid to gas or gas to liquid is vaporization. Solid to liquid, liquid to solid is called fusion. Latent heat of fusion or latent heat of vaporization. Alright, I'll just leave this on the slide here, so I think if there's some blanks you can copy, but it's not that dissimilar from boiling and melting and solidification. Alright, again, the definition of condensation, gas to liquid, put a star here without a change in temperature. You can pause the video anytime. I'm going to move on. Which brings us now to our new portion, which is called latent heat and specific latent heat. Alright, so let's discuss latent heat and latent heat fusion and specific latent heat. Now, there are two types of latent heats. We call them the fusion and vaporization. You should know by now which state is entailed. This one solid and liquid. This one is liquid and gas. Alright, so let's find out what latent heat of fusion is. So latent heat of fusion is the amount of thermal energy required to change a substance from solid to liquid without a change in temperature. You see this kind of definition I'm having again. Now, it is written as big LF. So capital L with a subscript F. Alright, it's not L times F. This just together means one symbol, LF. It's called the latent heat of fusion. Now, the amount of energy required to change an object from solid to liquid is called the latent heat of fusion. Q is the energy. The unit of the latent heat of fusion is joule because energy is in joules. Now, so for example, I have a 2 kilogram of water at 100 degrees Celsius. So 100 degrees Celsius is already at the boiling point. So when I supply energy, it will start to change state from liquid to gas. So the energy required is 8,000 joules. So if the energy required for me to change all of these 2 kilograms of water to gas is 8,000 joules, then I call this the latent heat. Sorry, this is not fusion, this is vaporization. Alright, so this is the latent heat. Latent heat is just the amount of energy required. It is energy essentially. Now, what on earth is specific latent heat then? Specific latent heat, just like its counterpart specific heat capacity, is written with the small version, so small l with a subscript f. It's the amount of energy required to change 1 kilogram or unit mass of the object, either 1 kilogram or 1 gram of the object, from solid to liquid without a change in temperature. Alright, so what is the link between latent heat of fusion and specific latent heat of fusion? So we discussed just now that latent heat of fusion is just the amount of energy required by an object to change its state, be it how big the object is. Now, specific latent heat is the amount of energy per unit mass or per kilogram. So let's look at this example. The same example, 2 kilograms of water, I want to change, is already at 100 degrees Celsius. I require 8,000 joules, and this 8,000 joules is the latent heat of fusion. The specific latent heat of fusion then, is just then 8,000 joules divided by 2 kilograms, which will give me 4,000 joules per kilogram. That means I need 4,000 joules to change just 1 kg of the object from liquid to gas. So this quantity here is called the specific latent heat of fusion, small LF. So this one, how do I calculate small LF? 8,000 is the latent heat of fusion divided by the mass. So if I were to write it out, small LF is equivalent to latent heat of fusion divided by the mass. And therefore the formula I need to remember is this. I just bring the M over, big LF equals to MLF. So remember that LF is just the energy. And that's how I get this. Q is equals to latent heat of fusion is equals to mass times specific latent heat of fusion. The latent heat of fusion units is joule per kilogram. Latent heat of fusion is joule. Now, I won't discuss about this because it's exactly the same thing. Latent heat of vaporization is from gas to liquid, between gases and liquids. The change of state from gas to liquid or liquid to gas. Latent heat of vaporization is written as big L subscript V. Specific latent heat is written as small l with a subscript V. And the only difference is that it's per unit mass, the same as the fusion version. Alright, and then we come to the formula again. It's still the same thing. The amount of energy required to change an object state from gas to liquid or liquid to gas is called the latent heat of vaporization, and is calculated by M multiplied by small LV, or specific latent heat of vaporization. Now, all these formulas may be a bit confusing. Alright, now before we go on to deal with even more complicated calculation, I thought it'd be useful to just have a look or summarize what we have learned so far in terms of specific heat capacity, latent heat, and all this. Alright, so let's look at this. This is a typical heating curve. Alright, I encourage you to draw something like this or create something like this so that it is similar. You can have it on hand for you to use. So at the start here, the state I have is a solid state. Alright, later on when it is at the melting point, then both solid and liquid will actually exist at the same time. This is being melted. Alright, beyond here only liquid exists. The temperature is increasing. At this portion of the graph where boiling is occurring, I have liquid state and gaseous state at the same point. And then over at this point where all the liquid has boiled away and changed to gas, and energy as supplied will then be used to increase the temperature of the gas. The processes involved, what are the name of the processes? Going this way, solid change to liquid is called melting. This portion is called freezing, or sometimes we use the term solidification. We also learned that the energy required for any processes that involve a change from solid to liquid or liquid to solid is called the latent heat of fusion. Alright, the processes involved with a change in state from liquid to gas, that process is called boiling. And the reverse of that process from gas to liquid is called condensation. The energy involved in changing liquid to gas or gas to liquid is called the latent heat of vaporization. Now, whenever we are talking about a temperature change, I'm increasing the temperature of a solid, you must remember that the thermal energy goes only to the kinetic energy of the molecule, which then results in a temperature change. Over at this point, all the energy that is being supplied goes into the potential energy instead of the molecule. And what is it used for? It's used to overcome the intermolecular forces of attraction. And when you are overcoming these intermolecular forces of attraction, then you have a change of state occurring. Now, overcoming, if you are going this way, meaning you are increasing temperature. If you are cooling it down, then we say we are forming intermolecular forces of attraction. Alright, I won't go into this because it's still the same thing as over here. Whenever I increase the temperature, it goes into the kinetic energy. The liquid to gas state just need to be a little bit careful because there are two forces involved. Not only does it have to overcome the intermolecular forces of attraction, it also has to overcome the force of the atmosphere, because as a object or as a liquid is trying to escape out into the gas, as a liquid is trying to escape out as a gas, you must know that there are invisible air particles that are moving constantly around, and they also exert a force downwards on this fella when it hits the surface. So this particle here must have enough energy to not only overcome the attraction due to the other molecules here, it also needs to overcome this. Alright, so it is useful for you to have something like this for your reference. Alright, let's carry on with the examples from latent heat and specific latent heat. Alright, you got a block of ice at 0 degrees Celsius. Left, the mass is 800 grams. This is the amount. How much energy is required to totally melt the ice? Then basically, if the specific latent heat of fusion is given, that means basically this number means is 3.4 times 10 to the power of 5 joules per kilogram. That means I need this amount of energy for 1 kilogram of the object. So for you to find the amount of total energy required to melt a 800 gram mass, then it's just using MLF. So if you do the calculation, then you get the answer as 2.72 times 10 to the power of 5 joules. Now, what is the latent heat of fusion? The latent heat of fusion, remember the definition is just the amount of energy required to melt an object. So you have already actually calculated the answer. So LF, remember, is equivalent to MLF, so it's equivalent to Q. So the answer is also 2.72 times 10 to the power of 5 joules. Alright, so I'm not gonna go through all the questions on specific heat, latent heat and specific latent heat of fusion and specific latent heat of fusion. So this question, I'm just gonna leave it here on the screen for a while for you to have a look if you want to, but I'm not gonna do all the questions. Alright, so just go on to this question here next. Alright, again with the question, give you a few seconds, gonna have a read. Alright, I got a 1 kilowatt heater immersed in 550 grams of crushed ice, which is at 0 degrees Celsius, left on for 5 minutes, and then the ice melts and the temperature rises to 49 degrees Celsius. Alright, so again, quite a simple question. 1000 watt. They ask you what is the total energy supplied by the heater. It's a 1000 watt heater. So remember point number 4 on the 5 points that you need to know. Energy equals to power times time. So you just calculate. Remember that when you're calculating energy and you are given power, you need to convert the minutes to seconds. So 5 times 60, and that will give you an answer of 3 times 10 to the power of 5 joules. Now, they ask you how much energy is required to raise the temperature of water from 0 to 49 degrees Celsius. So this portion is actually a temperature increase question. So it is not a change of state question. So actually you're supposed to use specific heat capacity. So again, what you learn, Q equals to MC delta theta. Make sure you use the correct mass of ice. It's 550 grams, but it's given here as kilogram. So please be careful when you are using this formula. So because this is given in kilogram, I change this to kilogram. So it's 0.55 kg times 4200 times the change in temperature is 0 to 49 degrees Celsius, and you get the answer as 113190 joules. Now, so this amount of energy is given by the heater. So the amount of energy required for you to just raise the water temperature from 0 to 49 is given as this one. So where else is the excess energy going to? Then the excess energy going to is actually going to melt the amount of energy required to melt this amount of ice. So we come up based on our principle of conservation of energy statement. The energy of the heater is used to melt the ice plus to increase the temperature by 49 degrees Celsius. So I already have this value. The energy of the heater is 3 times 10 to the power of 5 calculated here. The amount of energy required to melt is Q melt, and then the amount to increase the temperature by 49 degrees Celsius is given here. So 113190. So 3 times 10 to the power of 5 minus 113190 gives me my MLF, because the amount of energy required to melt is the mass times the specific latent heat of fusion. Alright, so this one is 0.55 kilogram of ice. Alright, and then this one you minus off, you get the value 186810. Then this is just the latent heat of fusion. Then simply just calculate the latent heat of fusion. Then it's 3.4 times 10 power 5 joule per kilogram. Right, moving on to the next question. This is the solution, just showing it to you. Alright, so again, I'm not going to go through all the questions again. So I'm just leaving this here. You can pause anytime you want. The solution is here for this question. Again, I'll leave it here. Alright, moving on. Alright. Not gonna go through this question, just have a look if you want to. Alright, next slide. Alright. And then I'll go through this last question. Okay, we can do this together. Alright, so a beaker contains 0.25 kilograms of water. Alright, and the water is at 10 degrees Celsius. You immerse a heater of 2 kilowatt in it. Find the time needed to turn the water completely into steam. Alright, so just remember that when you do this, start off, the main issue with this chapter is the setting up of the problem. So the amount of energy given out by the heater is used to, your initial start of the object was 0.250 kilogram of water at 10 degrees Celsius. So you want to find the time it takes for it to completely change to steam, meaning I need to change and increase this fella to 100 degrees Celsius first, then I need to boil. So the energy used by the heater, energy given out by the heater, is used to increase the temperature by 90 degrees Celsius from 10 to 100 degrees, plus then completely used to change the state of the water to steam. Alright, so if we just do the calculation, then energy is power times time. Then this change in temperature is actually a specific heat capacity question. So MC delta theta plus change of state. Then this is liquid to gas, so just be careful. You are actually using M, latent heat or specific latent heat of vaporization. Alright, 2 kilowatt means it's a 2000 watt power supply. You calculate the time. Mass of the water is given as kg and kg, so just be careful, change it to kg. 0.25 kg multiplied by the heat capacity. There's a lot of numbers, so just don't be confused. You are using this one. Again, they can be fancy with the units. This is actually kilojoules, so you need actually 4200 joules per kilogram. And then you multiply by the change in the temperature, which is 100 to 10 degrees Celsius to 100, so it's 90 degrees Celsius. So this is just the energy required to change the temperature from 10 to 100. Then you need to calculate the energy required to change the state of the fella. So again, MLV, mass is 0.25 kilogram. Then you multiply by the specific latent heat of vaporization, which is actually 2200, but it's kilojoules again, so be careful. So what you are looking at is 2200 multiplied by 1000. Alright, do your calculation and you get that the answer is 322.25 seconds. Alright, so now I get that the video is going long, so you have actually basically learned quite a few quantities, but it's only the same few concepts being repeated over and over again. So again, I stress that the difficult part of this chapter is actually not to do the calculation, but it's actually the setting up of the problem. Now, what do I do to help you with what do I do that when I have students who struggle with this kind of questions is actually I make them draw the heating curve and the cooling curve of a graph. So solid, whatever we have done, solid plus liquid, liquid plus gas, boiling or condensation at this point, and then gas. So I ask them then to actually trace the amount of energy, because the difficulty is trying to figure out what energies you need to calculate. So let's say I have ice at negative 20 degrees Celsius and I want to bring it up to water at 95 degrees Celsius. So what are the energies that I need to calculate? So if I know the melting points of the liquid, then all I do is I roughly find where on the heating curve this object is. Ice at negative 20 degrees Celsius is below its melting point, so it's somewhere around here. So I just put an indicator. This is it at negative 20 degrees Celsius, and then this is the start point, and the end point is water at 95 degrees Celsius. So it hasn't reached the boiling stage yet. It's in the liquid state. It's somewhere here, 95 degrees Celsius. So then all I need to do is to calculate the amount of energy for it to get from here, negative 20, to here, the amount of energy required, plus the amount of energy required to melt all the object, plus the amount of energy required to change that or increase the temperature of the liquid state of the object from 0 to 95 degrees Celsius. So by tracing this, I know there are 3 distinct energies that I need to calculate. Now, this is useful. You can copy this down later if you want. If you should have this printout already. I sent it to you. So this specific heat capacity, whenever I deal with temperature changes, I am calculating using specific heat capacity and heat capacity. When I'm dealing with melting or freezing or change of state, then I use latent heat of fusion, or I use the latent heat of vaporization. And the formula is, consequently, I use Q equals to MLF or Q equals to LF. Alright, whenever there's a change in temperature, again, be it liquid or be it gas, then I use specific heat capacity or heat capacity to calculate the amount of energy required. And the formulas involved is the specific heat capacity is Q equals to MC delta theta, or Q equals to latent heat or big C delta theta. Now, what happens when I have a challenging question that requires me to actually have 2 objects thrown together and then find the final temperature? We did a simpler example just now involving only specific heat capacity. Alright, so your role is actually very simple. I've listed down the steps. You identify the initial condition of the 2 materials. So what is the start condition of the 2 materials? Be it I have ice and then I have water. So you identify the 2 materials you want to mix, and what is the start condition of each of them. And then you identify the final condition of the mixture. So you should have the ice in the water. They will reach a temperature that is the same because they are in the same, they have reached a thermal equilibrium. Then after that, individually for the ice and for the water or the liquid, you calculate what is the energy it takes it to get there. So if let's say the ice totally melts and then reach 95, then you know that the amount of energy taken in by the ice is this amount. Then if let's say the liquid here drops from here, from a certain temperature to down here, it could be a different liquid for a certain temperature to down here, then all I need to do is to calculate the specific heat capacity of that. Alright, so after you have traced on each of them, trace for one of the material, trace for material 2, then I use the last step is use principle of conservation of energy and equate those 2 together. Now, how would that look like in question form? Let me just show you what it would mean. Alright, so this is a question found in your worksheet. Those of you who don't have, you can look at the screen. Alright, you got a glass of lemonade and then you put in ice. They tell you all of the ice melts. So they ask you to calculate what is the final temperature of the lemonade. So your setup of the problem should be something like this. Alright, you know that the object, you have 2 objects. One is a lemonade, 0.2 kilograms of lemonade at 30 degrees Celsius. Then you have 0.05 kilogram of ice at 0 degrees Celsius. And then after that, after they have reached thermal equilibrium, you know that they reach a certain temperature where the ice has totally melted and changed to water, and they both end up at a certain temperature, and this temperature is the same. You don't know what's the temperature, but you can call it T degrees Celsius. So then you go to you write down individually the cooling curve and the heating curve. So the lemonade will actually decrease in temperature, so you should draw a cooling curve. The ice instead will actually gain in temperature, so you should draw the heating curve for it. So then you identify where is it. So if I were to look closely at the lemonade will start off at, let's say, 30 degrees Celsius. Then after that it will cool down to a certain temperature. I do not know the temperature, T degrees Celsius. The ice started off at 0 degrees Celsius in its solid state because it is ice. So which portion of the heating curve is actually over here? It's all ice and it's at 0 degrees Celsius, its melting point. So, and then it ended up in the liquid state at some temperature, I do not know, but it ends up at T degrees Celsius. So now that my setup is enough, I know that the amount of energy I need to get from here to here is equivalent to the energy that the laminate needs to get from here to here. So then I just set up the problem and I write the solution. So the amount of energy gained by the ice is equivalent to the amount of energy lost by the lemonade. So for the ice, it actually has to melt first and then increase in temperature. So I write MLF, latent heat of fusion, use the latent heat of fusion formula, plus MC delta theta. For the lemonade, it doesn't have any change of state, it's only changing in temperature, so use just MC delta theta on this side. Then it's just a matter of plugging in the correct numbers, so make sure that you don't get confused. So the ice is actually 0.05 kilograms. Alright, then you multiply by the latent heat of fusion of the lemonade. Alright, I just flashed the question here again, you can have a look. Alright, the lemonade is 3.36 times 10 power of 5. So this is done. Then the MC delta theta for the ice, use 0.05 kg of ice. Then for the ice, I need to use the specific heat capacity of water. So it is 4.2 times 10 power 3. Then the temperature change is actually for the ice, is from T to 0. It's the temperature required to change from 0 to T. So it's T minus 0. Then all this is equal to the lemonade. The lemonade is actually 0.2 kg. Then you times by the specific heat capacity, 5.36 times 10 to the power 3. Then the temperature change it takes from here to here is 30 minus T. So you just draw 30 minus T. Alright, so then after that it's just a matter of expanding and solving it mathematically. Alright, I won't go through the rigors of all of it, but the final temperature is actually 12 degrees Celsius. So you can solve it yourself. Alright, so there's another question for similar question. This is possibly the more difficult type of question that you encounter in the O's. So I'll just leave the question here. Alright, you want to attempt, please do attempt. Alright, and then I'll move on to the next portion. So the last portion of the chapter is talking about evaporation. Now, when you have wet clothes, that means clothes that have water in them, why is it that it will dry out eventually? Where does the water go? The water doesn't disappear. The water obviously changes to its gaseous state from liquid to gas. But obviously it hasn't reached boiling point because, well, the environment is not 100 degrees Celsius. So where did all the water go? So this process of the changing of state from liquid to gas doesn't occur at boiling point of the liquid is called evaporation. Now, what on earth is evaporation? Evaporation is a process that is a change of state from liquid to gas. It requires thermal energy from the surroundings for it to do. Alright. You will notice what evaporation is because if you step out of the swimming pool on a very sunny day, your body will feel cold. It's the same effect when you go for an injection and they swap alcohol over your site, the injection site, then you feel that it's cold. It's the same reason because the alcohol or the water is evaporating from your skin. Alright, so why does this make you feel cold actually? So this is something that we're going to explore very quickly. Alright, so what exactly is evaporation? Alright, evaporation, the entirety of the explanation is here. You start off from kinetic model of matter. Molecules are in constant random motion. Alright, because they are in constant random motion, there will be a chance that there will be some molecules that will have enough energy to overcome the attractive forces due to if this is the surface of the liquid, attractive forces due to the molecules around it because there's intermolecular forces of attraction, and also the force of the atmosphere which is pushing it down. If it has enough energy to overcome all of this, then it will escape as a gas. Now, why is it that some molecules will have more energy, some of them will not. So basically, your molecules are just randomly moving, and they will collide in any manner and in all directions. So as you collide things together, there's going to be a chance that one fella will have more kinetic energy than the other. Alright, this is just because of the random nature. So sometimes you will have a molecule that goes off faster than the other one. Sometimes you will have both of them going off in the same speed. So because any collision will result in one fella gaining energy or some losing energy, then there's a chance that there will be a molecule who will continually gain energy from all this collision. And if he gains enough energy and he happens to be at the surface, and he has enough energy to overcome all of these two forces, intermolecular forces and forces of atmospheric pressure, then it will be able to escape as a gas. Now, the side effect of this is because this molecule here that is at the surface gains or gets all of its energy from the collisions that happen. So this molecule gives him energy, this molecule gives him energy during the collision, and he now has high Ke and able to escape. As an unintended result, all of these other molecules have given him energy, and whatever is left behind in the liquid is lower kinetic energy. And because it is lower kinetic energy, you know that kinetic energy is linked with temperature. When something cool evaporates out, it causes the whole liquid, the temperature to actually decrease. So this process is called evaporative cooling, and that's the reason why you feel cold when things evaporate on your body. Now, there are some important differences that you need to take note. This always appears in the O's. Boiling occurs at a particular temperature. Common mistake, students like to write 100 degrees Celsius. Only water boils at 100 degrees Celsius, so make sure you don't write this. It's at a particular temperature. Evaporation can occur at any temperature, because remember the mechanism is just due to the random collision. If you happen to have a molecule that suddenly collide so many times and it has enough energy to escape, then it will escape. Alright, it can occur at any temperature. Boiling is fast, evaporation will take a long time because of the random nature. Alright, boiling will take place throughout the whole liquid, but evaporation will only occur on the liquid surface. This one makes sense. If you have a particle that is due to the collision suddenly is in the center of the liquid and actually has enough energy for it to be able to escape. Right, as it's moving along, it will consequently crash with other molecules in the air and probably lose energy. So it will only happen, evaporation will only happen if it happens to have enough energy at the surface and will be able to escape. Alright, in boiling you'll see bubbles, evaporation you will not see bubbles. In boiling the temperature remains constant. In evaporation the temperature may change because the temperature usually will drop. In boiling you need some external energy source. In evaporation actually you do not need an energy source, because the energy is already in the liquid. It's just due to the random collision. If one guy has enough energy, he will just escape. Alright, so this one usually you need a random external energy source like the fire or something like that. Alright, what are some factors that affect evaporation? Humidity. The more humid it is, the more difficult it is for my molecule at the surface to be able to escape the water, because you got so many of these fellas who are already up there, and it's going to exert a greater force on him so that he cannot escape. He will need more energy to escape. The larger the surface area, the higher the rate of evaporation, because evaporation can only occur on the surface. The boiling point of the liquid, the lower the boiling point, the higher the rate of evaporation, because the lower the boiling point, it implies that the intermolecular forces of attraction are weaker. So therefore, I do not need to have so much energy to be able to escape, because the rest of the molecules are not holding on to me as tightly. Movement of air. If there's wind, then actually the rate of evaporation will increase. You can think of it as imparting energy to the molecules on the surface. Alright, the molecules, the air. Reducing atmospheric pressure will also increase the rate of evaporation, because you don't have so many of these molecules pushing down on the surface, preventing this vapor from escaping. And the higher the temperature, the greater the rate of evaporation. So if you have a liquid or water that is already at 99 degrees Celsius, it's almost there to boiling. So most of the particles already have a lot of energy. So the chances of you having a molecule that is able to overcome all these forces will be higher. So that's why the higher the temperature of the liquid, the greater the rate of evaporation. Alright, some applications. Alright, when you perspire, you will feel cooler. That's why humans perspire. It's not because the water coming up from my sweat pores is hot. It's because the evaporative cooling will then leave a layer of very cool water on your skin and it will cool you down. Alright, using water also again is to cool somebody down. A refrigerator, your aircon all uses things called evaporative cooling, but the newer aircon uses a condenser, so a little bit different. Alright, so I know this is a long video, but you finally come to the end of the video. So I just leave this last slide here for you if you need to copy any notes. But that's it. Now, just a last point. There's not a lot of difficult concepts in this chapter, but the setting up of the problem when you are solving a specific heat capacity and specific latent heat question is difficult. That is the main difficulty of this chapter and the challenges. So I would advise that you follow this and use this to help you solve any calculation questions involving specific heat capacity and specific latent heat. Alright, bye.